one-line diagram. You guys have this one, so do me a favor. Here's how I have for one-line diagram for you right now. Okay, so you guys have, everybody has this view. Everybody has this view. The reason why I drew this view for you, I usually go over it, and I went over it twice. I want you to fully understand that the power system that we're using for this building is 208 120 system. It's coming from a Y, and it's grounded. Can I have thumbs up, Chad? This is the transformer that you tomorrow, Carrie, you're going to grab and you drop outside the building in Revit. It's going to be a delta, it's a Y grounded transformer. Can I have thumbs up, Chad? Now, where is the primary of this transformer? I'm only showing the secondary. Where's the transformer primary? I'm just going to sketch very slowly the transformer primary. It's going to look something like this, and it's going to be coming directly from here. Phase A, phase B, and phase C. And I care less because that's the utility type. Cool? So this is the transformer that's sitting outside. This is your XFR. XFR is abbreviation for transformer. That's the one that's going to sit outside for your building. XFR. Any question, guys? Any comment? Okay. Now, your system is going to sit like this. So I have a 4-wire system with a neutral. Can you guys see the neutral coming in? How many wires you bring from the transformer into your panel? 4 wires. 3-phase and neutral. What happened to the ground and the grounding? Nothing. Mistake number 1, between the utility transformer and your building, you only carry 4 wires. The 3 hots and a neutral. Cool? Then, right in here, I threw a couple of different types of loads that you can feed from the 208 120 Y grounded. You can feed 3-phase 208 system, no neutral. You can feed single-phase 208 system, no neutral. And you can feed single-phase 120 system. These are the 3 types of loads that you can feed from this system. Can you have thumbs up, Aaron, my friend, about these 3 systems that you can feed? The most confusing things, guys, for people is they don't understand a system like this can get you 3-phase 208, can get you single-phase 208, just 2 hots, and can get you single-phase 120. Okay? Everybody's okay with that? Depends on when you take the 3-phase, you got 3-phase. You take 2 phases, any 2 phases, you got single-phase 208. If you got any phase and a neutral, what do you get? 120. Okay, I put 3 pole circuit breakers here, I put 2 pole circuit breakers here, and I put single pole circuit breakers here. Everybody knows why? Every time you have a hot, what do you need? A pole for circuit breaker. Any question about this diagram? And these are 3 conductors, these are 2 conductors, these are 2 conductors. Everybody can see the difference. When you guys are walking through circuiting, these 3 types of loads you're going to be circuiting from this system. You see with phase A, B, C, and all this good stuff. Any comment about this slide? Do you guys fully understand this, or you need a refund? No, fully understand it, Aaron, my friend? Okay, so that's the first important thing. The second thing, I want to modify the riser, guys, because we changed it slightly, and I want you to modify it with me. Your riser is going to look like this. For moving on, I'm going to modify my riser to slightly adjust it. I'm going to have main panel here. Oops, let's use a different color here. So I'm going to modify it, and you can see where I'm modifying here, so you can get the hang of it. I'm going to put my main panel here. This is main panel, and I'm going to bring my and then right next to it, here's what I want to add. I want to add everybody in black, the stuff that I want to add. I want to have right in here, guys, auto transfer switch. Auto transfer switch, because we are using an auto transfer switch now. And your riser, you're going to come from here to the auto transfer switch, out of the auto transfer switch into the panel, and from the panel, you're going to go to the other panels. Oops, let's just modify this one to make it more realistic here. So can you guys modify it, please? There you go, and here you go, and here you go. Okay, so that's basically how your fixture is going to look like. This one is going to be PVC, definitely. Everything else is EMT. Can you guys see that? I have an auto transfer switch feeding main panel. The 2 panels are feeding 200 amp. And my lighting panel, Jeff, we changed it into what? You guys remember? 225 amp. Please change that one to 225 amp panel. And so when you build your riser tomorrow, and this has to be 500 amp, 500 amp. When you guys sizing your system, your riser is going to look exactly like this tomorrow in Revit. Cool? Now, the other thing I want to add right in here, right next to, is a generator. Right in here, generator. And the generator is going to come directly from here underground all the way to, all the way to the auto transfer switch. So I have a generator. Oops. Okay, when it does that for you. So I'm going to have here, and this is going to go all the way directly, and this is my generator. We're still underground here, and these two are going to be PVC. This is PVC. Cool? PVC. Any question, guys? We have a generator. We added a generator, and the last thing I want to do, guys, I have a termination box. I'm going to add it right here. I'm going to add termination box or meter box, meter terminal right here. I'm going to modify this into go to the meter terminal first, and then out of the meter terminal, I'm going to go directly into the building. So let's do it this way. And then I'm going to grab, it's a lot of changes, huh? Okay, you're going to see the outcome in a second here. Going in here, and this is coming in, and this is coming in. There you go. That's how it's going to look like, ultimately, hopefully. We don't change it more. Okay. So that's meter. So these are underground. Anything underground, guys, will be underground. So I'm going to have, this is PVC, and these are PVC. Okay. Any question, guys? So I have a transformer. I went into the termination meter terminals, or termination box. Out of the termination box, I got into the building, the auto transfer switch. Out of the auto transfer switch, I fed my 500 amp panel, and I fed the two receptacle and lighting panels from it. And then I have a generator that I went directly into the auto transfer switch, because the generator is going to flip between both of them. So that's basically what you're going to have tomorrow when you build your system. Did you guys modify this one slightly to look something similar to this? Yes, no? We're going to be dropping these fixtures tomorrow. Okay, the generator, let me throw a couple of sizes for you. Let's pick a couple of sizes, guys, for you, so we can throw them tomorrow. Transformer. So it's full load 3-phase. If you guys take, we don't size the transformer, but if you take the 500 amp, multiply it by 1.73, multiply it by 208, equal, divide by 1,000, you're going to end up with 178 kVA. So the system is going to eat 178 kVA. Cool? kVA. So then my transformer is going to be able to get me 178 kVA. But if you guys go to the transformer right here, which we will be sizing, I have to go to 225. So for the time being, do me a favor. This is going to be 225 kVA. Who cares if that was a one-line diagram with CAD? We don't care. We don't care in CAD. But in Revit, Joe, you need to go actually pick a kVA size of the transformer when you drop it tomorrow. So can you guys pick 225? How did I come up with the 225? You take the 500, which is the size of the panel, multiplied by 208, multiplied by 1.73, divided by 1,000, get you 180. The next standard transformer is 225 kVA. We don't size this, the utility size it. We're just dropping it in there, guys, so we can show a riser. Okay. So the same token, I don't have a size of a generator size. The same token, guys, with your generator, make sure your generator can also get closer to 225 kVA. Can we size a generator to 225 kVA? When we drop the generator, something similar to this, 225 kVA. So these are the sizes you're going to drop. Now, your auto transfer switch you're going to drop tomorrow, the auto transfer switch, which is that boy here, this is going to be also 500 amp. Most likely it's going to be a 600 amp because we don't have a 500 amp. It's going to be a 600 amp because we don't have a 500 amp. Can you guys, everybody has the sizes that you need? All the sizes that you need for the riser? Any question is about the riser that we need to drop tomorrow? So tomorrow you're going to drop a generator outside. You're going to drop a transformer outside. You're going to drop a termination box, meter box outside. You're going to go inside the building. We're going to drop an auto transfer switch and a main panel 500 and a lighting panel 225 and a receptacle panel 100. Then we're done dropping them in Revit. Cool? Okay, that's your riser. So please modify it for tomorrow when we start doing that. Okay, and I gave you sizes. The reason why I gave you the sizes right away, because when you try to grab something tomorrow, Darren, it will ask you what size KVA do you want, right in the spot. I don't want you to sit there and start sizing here. We'll go through the sizing, guys, as we go, but I want you to be ready so you drop and play. Okay, that's what I want you to, that's how your riser is. Now, what this exercise about is, guys, taking a 3/4 inch EMT conduit from here and filling it with wires from the receptacle panel or the lighting panel and feed the branch circuit. So that's what I'm going to talk next about the branch circuits. I want to remind you, Andrew, everything above ground, all the stuff above ground is going to be what type of conduit? EMT. Everything below ground is going to be what type of conduit? PVC. Okay? All right, any question about the riser? All what we need to do it tomorrow, Kerry, is just drop that sucker into Revit. Really. The rest of the presentation is about this right in here. Can you guys see that 3/4 inch conduit that's coming out of the panel, out of this panel? And I'm going to see how many conductors I can put in these 3/4 inch. And how many circuits and how do you circuit, okay? So before I leave the riser, power riser. My power riser. Any question, guys, about before I leave my power riser? I want to remind you that the voltage system of everything here is going to be, because they're going to ask about voltage tomorrow. Everything as you drop the fixture, they're going to ask about what's the voltage. Anybody can give me what the voltage of the system that we're using? What's the voltage? 480, 277, or 208, 120? Everything. Thank you. The voltage system is 208/120 volt at 3-phase. So as you guys pick the equipment, please pay attention when you bring a panel. It will tell you, do you need a 480, 277 or 208/120? Which one are you guys gonna pick? 208/120. Okay.
On the outside of the wall.
That one here, that's a meter terminal. Because we're higher than a 400 amp or 200 amp. You have to terminate into a CT cabinet. It's a CT cabinet. Meter terminal box, CT cabinet. That's where you guys, because we're higher than 200 amp, they bring the conductors into a CT cabinet, current transformers, measure, and right in here, as a matter of fact, I don't know how we're going to do that in Revit, but it's going to be a meter here. Can you guys see that right to the top of it? It's going to be a meter. That's how you measure the current. Can I move on from the riser? Cool. Okay, now moving into the second slide. Now circuiting and grouping. Everything I'm going to go from now on is opinion. Everybody understand? Opinion. Opinions are opinions, okay? Based on my sound judgment as an engineer. You can find somebody who disagree or agree with that one. Okay, grouping, circuiting, and grouping. All receptacle circuits must be grouped. When you take circuits to feed receptacles, the best way in conduits, you have to group them, right? You group them in a conduit. All your lighting circuits, all equipment circuit 20 amp or less, which take number 12. Can everybody understand what I mean here? If you have receptacles to feed from a receptacle panel, the best way to do it is to do this, is to come over here, take 3/4 of an inch from the panel with how many conductors you can fit in these 3/4 of an inch, and go there and feed all the receptacle circuits. Can I have thumbs up? We understand that, Chad? Cool. Same thing for lights, lighting panel. So go back here. When you have your lighting panel, you take a conduit, a tiny little conduit here, 3/4 of an inch, and you feed all your lights by grouping the 20 amp circuits that's coming out of it. Cool? And my judgment also, if you have equipment, dedicated equipment circuit, guys, also group them. For example, a vending machine there, need a dedicated circuit for it. Also group them, put them in the same conduit. Cool? Now this is talk of a contractor, not an engineer. Engineers, we care less. We just throw a circuit and call the electrician will circuit it. Contractor, you need to know how to group them. How are you going to take all these 20 circuits, each one of them is 15 amp or 20 amp, out of this circuit into everywhere else in the building? That's where grouping become a big deal. Okay, can I get you to understand what all the receptacle, all lights, all equipment, 20 amp or less, it's a very good idea to group them as they come out of the conduit. Thumbs up, Chad? We understand that? Okay. Now, typical grouping. Here's a typical grouping. I showed you a typical grouping. Feel free to agree or disagree. I came from my receptacle panel. Here's typical grouping. I got from a receptacle panel into 3/4 of an inch. You don't want to put 1/2 inch. Always 3/4 of an inch. Into a J box, 4x4. Deep box is a good idea. 4x4. So we came out of this panel here into the ceiling, right in here. Okay, in a 4 box, and from this ceiling, I can take another 3/4 of an inch to go to another J box, another 3/4 of an inch to go down to a receptacle, or sometimes we go down with a 1/2 inch if we're going down to a receptacle, from the top down to feed the receptacle. We pick it up with 1/2 inch, 1/2 inch. But that's typically when you deal with conduits, you take a 3/4 of an inch to a J box in the ceiling, and from there you spread. You go to another J box, a third J box, and you start picking up these receptacles. Go here, down, drop, pick up receptacle, drop, pick up receptacle. That's one way of doing it. The other way is, of course, you move horizontal in a conduit, in a wall. Depending upon the wall like this, you can't move horizontal. You have to come from the top right through the cavity of these blocks here and go pick up the receptacle one at a time. So I showed you just typically physical, how are you going to do that in the field, right? So if you, what I'm interested in here, from here down, you're going to be an electrician to handle it. From here up, always get into the habit of grouping the 3/4 of an inch, come with a 3/4 of an inch or an inch sometimes, and grouping the circuits inside it. You're going to know why I picked the 3/4 of an inch in a second. Any question, guys, about typical grouping circuits? Okay, now, I want you to keep this in mind, and these are the things that I suggest you group. Now, you have an air handling unit. Is it a good idea to group the feeder for an air handling unit with other circuits? No, bad idea. We're talking about 20 amp circuit, lighting circuit, and 20 amp receptacle circuit, and 20 amp equipment circuit. That's it. That's where grouping makes sense. All these are, which color am I here? The 20 amp, we're talking about 20 amp circuits. 20 amp, and these are typically 20 amp. These are the type of the circuits that we're talking about, guys. Can I have thumbs up, Chair? We fully understand. We're not grouping the air handling unit. Okay, now moving on. Let's go. Here's an example that I showed why I use personally 3/4 of an inch. An example. Take this. I have an EMP conduit 3/4 of an inch. How many conductors? Number THHN from Annex C1, page 744, NEC 2011. If you guys go to 3/4 of an inch EMP, you're going to find that you can put 16 conductors in this conduit, maximum. Can I have thumbs up, chat? That's easy. From this Annex C1, 16 conductors, why THHN? We're inside the building, right? We're doing branch circuit. Okay. Tight fit is going to be the judgment. We're going to the max here. Cool? Let's just hold your horses with me. So that's going to be your maximum that you can pull is 60. Cool? Now take this. Here's what I suggest. Here's your conduit, 3/4 of an inch here. This is my conduit. 3/4 of an inch EMT. Okay, now do the rating. Let's use the rating here. I have number 12, 310.15 B16, 90 degree, give you what? 30 amps. I'm going to do it. Okay? Now, here's what I suggest. Not suggest. The maximum you can carry, the maximum circuits that you can carry inside this conduit. Let me explain. So you have 20 amp circuit for 6 continuous. Everybody, why do you think I'm pulling 16 out of a 20 amp circuit? Continuous, you can't take more than 80% of the rating of the circuit breaker. So I have a 3-pole or 3 single pole circuit breaker tied together with a common neutral here, with a common neutral. 1, 2, 3, 4. 4 times 4 is how many conductors? 16. So I can put, can you guys look at this? I can put 16 circuits into a 3/4 of an inch and carry them with 16 conductors. I'm sorry, 12 circuits. 1, 2, 3, 4, 4 times 3, 12 circuits. One more time. Look at this circuit here. I have 3 20 amp circuits, 3 20 amp circuits, right? 3 20 amp circuits tied together. Each one of them can only provide 16 amps because it's continuous. So I can have 3 grouped together with a neutral, 3 grouped together with neutral, 3 grouped together with neutral, 3 grouped together with neutral. Can I have thumbs up? We understand what you're doing, Chad? Yes? No? Okay. Now, how many carrying conductor do I have here? Assuming these are feeding harmonics and the neutral count. The neutral count. How many of them do I have? I have 4, 4, 4, 4. 4 times 4 is what? 16. Okay? All right, so take number 12 conductor, give you 30 amps. 16 carrying conductors. Everybody knows why 16? Because all these circuits that you're looking at, I group them with one conduit. Okay, so 50 amp, 50 times 30 will give you 15 amps. How many amps have I lost by grouping them? How many amps? This is how many amps you lose when you group them. And this is how many amps maximum they can carry anyway. How many amps did they lose by grouping them? 1 amp. Do you see why grouping them is not a big deal in terms of the rating? I use this one, guys, so I lost only 1 amp. By grouping all these 16, all these 12 circuits, 12 20 amp circuits. If you guys understand this, you will understand the 3-phase circuiting completely. So I have 3 20 amp circuits tied together, 3 20 amp circuits tied together, 3 20 amp circuits tied together, 3 20 amp circuits tied together. These are multi-wire branch circuit 1, multi-wire branch circuit 2, multi-wire branch circuit 3, multi-wire branch circuit 4. All of them are grouped in a conduit, 3/4 of an inch conduit here. And I know these are 16 conductors. Have I maxed my conduit? Yep, I maxed my conduit. I didn't exceed it. So conduit fill, I'm good. Now let's see about the rating. So conduit fill, yep, I'm 16 conductors, I'm 16, right? Conduit fill, okay. How about grouping, the rating, right? If you do the rating, you end up with 15. So if you group them all together, you only lost 1 amp. So the only thing I do that one, just to get you an idea, is always group your circuits. Can you have thumbs up, Chad? Now if you pull neutral with each one of them, that will be how many? That will be, each one of them will be 6. Then you have to recalculate the formula, right? It's a different story if you pull neutral with each one of them. Okay, any question, guys, about this? So here's what I would do. Personally, I would pull, instead of pulling these 4, I will pull 3 of them, and I leave this one for what? Future. That's a good design. So instead of putting all these 4 in one conduit, I put 3 of them in one conduit. So 3 times 4 give me 12 conductors. So I'll have 12 conductors. I still can go another 4, right? Another full circuit if I need to in the future. So that's a good design. 3-phase circuits, and this could be receptacles or what? Or lights. No problem. Receptacles, lights, or small equipments. Small equipments, 20 amp or less. Receptacles, lights, or small equipment. Can you have a thumbs up, Chad? We fully understand that one? Okay, so what's this piece then? Future. So how many circuits you want to group in a 3/4 of an inch? 9 circuits. Where do the 9 come from? 3 plus 3, 6 plus 3, 9. And this boy here is for what? For future use. Any question, guys? I want you to pay attention to the number 15 here, though. That's why the number that I use always for sizing, number 15. I only lost 1 amp. Remember, 1 amp is not a big deal by grouping them. Cool? Even if you did not group them, you can't go higher than 16 amps anyway, even if you want to. Any question, guys, about this slide? You see why I threw this slide for you? Okay, so let's go to the next one. Now, here's what judgment. I have the main panel, the receptacle panel, and the lighting panel. And I gave you guys suggestions. Let's start from here. Receptacle panels. On a 20 amp circuit, 2 conductors number 12, you can fit 6 receptacles. Why? Now remember, we are feeding receptacles in an office type building. You're going to see why 6 in a second. Can I have thumbs up, Chad? We understand that 6 of them I fit here. Cool. I have vending machine. I have a vending machine. This is my vending machine, right? And I need, so for a vending machine, what good design? What do you do for a vending machine? Dedicated individual branch circuit. Can you guys see that? Number 20 amp, 12, number 12 conductor, dedicated vending machine. Can I have thumbs up, Chad? Cool. Come over here for outdoor receptacles, outdoor receptacles. Outdoor receptacles, I typically don't have a whole lot of outdoor receptacles. My rule of thumb is if you have in a commercial building, up to 3 receptacles, throw them in a 20 amp circuit. Now, can you put 4? Yes. These are what? Good judgment. Outdoor receptacles, throw them in a 20 amp. Now, you have an exhausting fan sitting right there, a tiny exhausting fan that need a 20 amp circuit. What do you do with it? Shoot for that one individual circuit. Can you have thumbs up, Chad? How we do that? One more time. In a receptacle panel, the receptacles in the counter in the office, 6, no more than 6 in one circuit. When I say receptacle, guys, these are duplex or single receptacles. The quad count as 2. Cool? So for receptacles, here's my receptacles, 6 on one circuit. Thumbs up? Cool. If vending machine and any machine type, dedicated circuit. Then we go to the outdoor receptacles, throw 3 on one circuit in a commercial building. If you have another 3, throw them in another circuit. Okay? Exhaust fan, tiny little exhaust fan, put it in one circuit. Okay? Let's go to lights. This is for the receptacle panel. These are typical loads on the receptacle panel for this project. Can I have thumbs up over the receptacle panel? Switch to the lighting panel. For the lighting panel, here's what I suggest. And you're going to see why 18 fixtures. These are the number of fixtures you're going to feed from, again, design-wise, you're going to see why I did the 18 in a second here. So is it 6 and 18 fixtures? So you count 1, 2, 3, 4, 5, 6, 7, 8, 18 fixtures. You feed them from what? One 20 amp circuit with 2 conductors number 12. Can I have thumbs up, Chad? We're going to know why 18 in a second. Okay, now we went to the parking lot. Now the parking lot lights, you can put up to 7 on one circuit. Generally speaking. Can I have thumbs up, Chad? Why 7? We're going to know in a second. Can anybody tell me why in the parking lot I pulled 2 number 8, even though I have 20 amp circuit going to the parking lot? Voltage drop. Thank you, voltage drop. When you go to the parking lot, that's the only, you don't pull anything with at least number 8. Sometimes we pull 4 out even. So number 8, number 10, number 8 is common. So when you go to the parking lot, your conductors are going to be number 8. Why? Voltage drop. Okay? That's why I put the voltage drop. Any question about lighting panel and receptacle panel, typical loads? These are typical loads for your project or any project. Can I have thumbs up, Chad? Cool. Let's move into the main panel. Now, when we move to the main panel, now these are big boys. In the main panel, there will be big boys here. Big boy number 1 is cooling unit. Cooling unit, that's a big boy. It's a dedicated circuit. It's 110 amps and 3 conductors number 3. Where the heck did I come up with this? You're going to see the calculation that's coming. Very easy. Then 30 kVA heater. I have a 30 kVA heater, guys. I fit this one from, what's the circuit for that boy? Now remember, these are 3-pole. I have 3 conductors number 2 for the 30 kVA heater. I can't remember what the overcapacity device here. Is it 30 amps? I think we're going to do that one in a second. We're going to come into this. And then I have a 2 horsepower boiler pump, and I fit this one from a 20 amp circuit 3-phase. From a 20 amp circuit 3-phase. How the heck did I come up with these sizes here for grand circuit? You're going to see in the next slide. Okay? So these receptacle panel, lighting panel, there's calculation coming, guys, to verify these numbers. Why did it come up with what they came up with? Can I have thumbs up, Chad? We understand? The reason why I threw these one for you, because that's the most important things for us. We know how to size the feeder and the branch, the feeder and the service. You guys know, because you did it for me. Now we're going to go down to the branch circuits and size them. Cool? Can you guys remember just the 6 receptacles and the 18 and dedicated circuit for these numbers that we throw here? Remember them when you start circuiting later on? You're going to have the slide here with you. Okay, let's go and verify what Chad have done. Let me tell you what my verification. And again, take it to your boss, Andrew, and at ACE, and they might tell you that guy's knucklehead. No problem. It wouldn't be the first. Receptacle circuits. Here's the calculation. Now I came up with these numbers based on the following. I have a receptacle circuit. You will be a fool to pull less than a 20 amp receptacle circuit in a commercial building. Do we agree on that one? 15 amp out the window. Doesn't exist. Can I? Yes. Should I? No. Why? Because it's a fool. You're losing copper. You're putting a lot of copper for nothing. So a 20 amp circuit, that's my cutoff. So general receptacles. If you do general receptacles based on the code, you take a 20 amp circuit, right? Multiplied by 120, right? Everybody knows where the 20 came from. That's the amps. Where the 120 came from? We burn the receptacles in the US at 120, the convenient receptacle. Divide by 180 volt. Does that ring a bell to you, the 180 volt amp? That's the one that we use for all the calculation for receptacles. Get you 13 receptacles maximum. Maximum 13, no matter what you do. And the reason why we use 20 amp here, because receptacles general purpose are not considered continuous. So we use 20. So here's your max. No matter what you do by code, you can't put more than 13 receptacles on a 20 amp circuit, right? That's the max. Now design. Now remember, we're engineers. When we design it in a commercial building. This factor that you have see here, it's called CSK. Anybody knows what CSK is? This is my initials. So if somebody asks you where the heck did that number came from, tell them Chad. Design factor. Design factor. Remember, these are commercial building. These circuits can be overloaded in a commercial building. They're used, some of them, general use in in offices and so forth. So you throw a 50 amp derating factor. If you take 50 of 30, what do you get? 6 receptacles. 6 receptacles. That's where the number 6 came to be. Can I have thumbs up, Chad? Now, if you go to your boss, Joe, and they say, you know what? I'm going to go to the max. Is it wrong? No. Everybody understands? So basically, the good design is 6. Now, if you have 1 receptacle, can I add it and make them 7? Not a big deal. But you have to shoot for how many receptacles for this project? 6 of them. Can I have thumbs up, Chad, where the 6 came from? For a piece of cake. Let's go to the equipment. Now, these are the receptacles. Equipment. Plugged in equipment as in vending machine. Vending machine. In your case, Jeff, it's going to be a copy machine, right? A big printing copy machine. That's also a dedicated circuit. So these are where you provide a dedicated circuit. I have a 20 amp individual circuit, a 20 amp for each machine. Everybody knows why? Like dishwasher, plotter, printer, office pot, the coffee pot, vending machine. These are examples where you have to provide a 20 amp dedicated circuit for each one of these vending machines. Thumbs up, Chad? Do you understand why? Why do you think we have a vending machine? It rushes high on it and it sucks a lot of amps. You know, so I don't want to share it with other receptacles. Even though I could, it's not a good idea to design a vending machine receptacle that's shared with other receptacles. Every vending machine shoot it at 20 amp circuit. Thumbs up, Chad? Okay. Dishwasher, same thing. Plotter, same thing. These are equipment that you guys have in your office. A printer, no problem. Yup, dedicated circuit for the printer. And the office, the coffee pot. This is not office, this is coffee. The office coffee pot. Coffee pot, it's going to have what? Dedicated circuit. Thumbs up, Chad? These are the good design. Now, can I put the coffee pot and the printer on the 20 amp circuit? I bet you if you do the math on it, you can. Not a good idea. Not, remember, we are designers. Good design. Can I have thumbs up, Chad, where we came individual circuits for the equipment? Now, when we start circuit, Aaron, my friend, and you start throwing the receptacle and you see a plotter, and there's a, how am I going to circuit this receptacle for the plotter, Chad? Individual circuit. Pick it up, put it in a 20 amp circuit, move on. Okay? All right, so any question about these guys' receptacles? Let's go to the next. Now, outdoor area. This is what I call it. Again, these are my opinion, and in this almost a lot of people agree with that one. Areas. I call these areas, guys, for receptacles. Areas like bathroom, outdoor, machine room, individual circuits. That's my opinion. For example, I have 3 receptacles in the outside of the building for outdoor. It's a very good idea to give them a dedicated circuit, not sharing with others. Design, remember, design. Code-wise, I still can do the 13. Everybody understand? My bathroom, I have a bathroom. 1 or 2 bathroom, you guys. You're going to have 1 receptacle for each bathroom. A good idea, dedicated circuit for the 2 bathrooms that we have, right? Can you have thumbs up, the male-female bathroom? 1 receptacle. C is area, and one of the areas is bathroom, outdoors, and machine room. Machine is the mechanical room. The mechanical room that we have, it's going to have a couple of receptacles. These are a great idea to put a receptacle for them. Why the mechanical room? Mechanical room, guys, this receptacle will be used for all maintaining the mechanical equipment there. So it's a good idea to put it in a 20 amp circuit by itself. Can you have thumbs up, Chad? We understand that circuiting. I want you to keep this dear to your heart, guys, as we start circuiting, because that's the base for circuiting. Okay, that's it for receptacles. Let's move to lights. Can we move to lights? Any question about receptacles before we move to lights? Okay, lights. Here's how I do lights, Kerry. 20 amp circuit full if you don't. 20 amp circuit minimum. 15 amps. Anybody knows where the 15 amp? Chad came up with the 15 amp. Why not 16? Do you remember, guys, when we grouped them? When we grouped them and we did the calculation based on grouping, you remember that 15 amp? I'm going to take into consideration that they're grouping them. And I'm limited to 15 amps. Can I have thumbs up? We understand where the 15 amps came to be? Cool. So that's where the 15 amps, grouping them. Go all the way, go all the way. Okay, here's my 15 amps. 20 amp, 15 amps can only pull 15 amps. Multiply by 120, give you 1800 volt amp. That's as the maximum you can pull out of this circuit, 1800 volt amp. Then here's how you do. Take the volt amp of each fixture. Volt amp, fixture 1, fixture 2, fixture 3, add them all up. They have to equal or less than 1800 volt amp, right? Right? Or you use a rule of thumb, design rule of thumb, which take the 15 amp, multiply by 120, divide by 100. Where the heck is the 100 came to be? 100 volt amp. Typical fixture like this, guys, typically they are around 96 volt amp. How do I know? Because we install them all the time. 96. So on average, if you have, especially with the energy code right now, this is even very high. You know what I mean? On average, the fixtures that you use, a lighting fixture in a commercial building, on average, 100 volt amp is good approximation for it. So if you take 100 volt amp, multiply it by this, how many do you get? 18 fixtures. Can I have thumbs up, Chad? That's where you got the 18 fixtures. Should I allow for future expansion on that one? Some people will say, well, typically my idea about lights, if you need a light is easy in the ceiling, guys. Because they're easy in the ceiling. If you want to add another couple of lights, easy to pull conductors in the ceiling and go to pick a couple of lights, another brand circuit basically. So 18 is very conservative. You can even put more on that. So 18 fixtures on one circuit, unless you do the calculation like I did here. So if you use VFDs later on, you say, Chad, I was able to put 30 of them on one circuit because I added the volt amp of all these my VFDs, and I put them on and they don't exceed this number, so I can put 30 of them. Cool? So for the time being, for our design, what's our magic number for circuits? 18 of them. Can I have thumbs up, Chad? Yes, no? Okay. All right, so let's go to, this is lighting, 8 on the 20 amp circuit. Parameters. Perimeter lights. The perimeter lights, guys, these are security lights around the building. Typically the same thing, 100 volt amp. So I threw another 18. If you have 18 of them around the building, put as a branch circuit for them and feed them up to 18. Higher than 18, what do? Another branch circuit. So if you came up with 21 lights, it's a good idea to split them, even from a maintenance point of view, guys. From a maintenance point, 21 fixtures are around the building. Split them into 2 circuits. 21 fixtures in one area. Split them into 2 circuits. Does that make sense?
So you do perimeter lighting the same thing you do the indoor lighting?
Yes, based on the same criteria, 100 volt amp assumption. Parking lot. Here's the parking lot. 20 amp circuit, always. 15 times 120 divides. Where the heck did I came up with 250 volt amp? Typically, metal halide, guys, in a parking lot, typical, unless you know otherwise, typically 250 is what we use for type of commercial. So if you divide by 250, how many of them you can get? 7 of them. 7 fixtures outdoor in 1 circuit. You have 8, split them. 2 circuits. Can I have thumbs up, Chad? Any question, Kerry, Andrew, my friend? Cool. Does it make sense? For circuiting, as you circuit these are the rules that you're going to be using for circuiting this building. Moving on. Any question about lights? That's the lights that you're going to encounter. You're going to enter parking lot light, perimeter light, and indoor. Can you please keep this handy as you start circuiting? So here's what Chad told us. 7, 1, 2, 3, 4, 5, 6, 7, 1 circuit. Flip to the other. Now you come up with 8 fixtures in the parking lot. What do? Thank you. 4 on 1 circuit, 4 on the other circuit. Okay? Unless you prove to me that they can fit in the same circuit. How do you prove to me? You're going to find the volt amp for all of them, add them up, and less than the 1800 that we did. Okay, now, any question about receptacles? See how easy for receptacles on lights? Done deal. Now let's go to motors given. Now these are motors. Motors, the information is given, and either 3-phase or single phase. Take this, I gave you one example. I gave you boiler pump number 1, 2 horsepower, 2A, 3-phase. Okay? Now remember how to do branch circuits for motors? These are given. So here's a 2 horsepower dedicated circuit from 430 to 250 to 8 give you 7.5 amps. You guys remember how we did the calc for the motors? We did that. And then you take 7.5 multiplied by 2.5. Why 2.5? It's a motor. You end up with 18.8, and the next standard is what? 20 amp. 20 amp. So that's how you do the branch circuit for motors. You size, this is how we size the overcome protection device, 20 amps. Any question, guys, about this? The overcome protection device 2.5. Why? Because we've done many of them. That's a dedicated circuit. Do we group them? If there are 20 amps or less, you can group them. But do we put multiple fans on one circuit? Not a good idea. Not design-wise. Any question, guys, for this motor? Typical motor I picked up. So let's look at the conductor. Branch circuits. The same thing. You take 1.25 times 7.5 give you 9.4. 9.4 give you number 14 conductor. What did they say about using number 14 in a commercial building? No. So why do we, then what do we flip it to? Number 12. Why 3 conductors? 3-phase. Can you guys see how I did an example for you for the pump? That's how you're going to do the branch circuit. I took the boiler pump number 1, take the full load current, find the overcome protection device, 20 amps. Then the same thing, find the conductors, multiply by 1.25, get you this, 14, no 14, we don't use it, we use number 12. Thumbs up, Chad? Typical calculation. Okay, here's another example. That's not good enough for you. Exhaust fan. I have one exhaust fan, number 1, it's a quarter horsepower, 120. If you guys go to the full load current of that one, the full load current of from the NEC code book is 5.8. If you go to the NEC code book, it's 5.8. Multiplied by 2.5, give you 14.5 amp. I end up with a 15 amp circuit breaker, and you calculate, this is single phase. Remember, these are single phase. And 1.25 gets you 7.3, number 14. So a 15 amp, number 14. Here's where I use my judgment. What did we say we don't want to use? We don't want to use number 14 conductor, and we don't want to use a 20 amp circuit. So these are judgment. I up this to 20 amp circuit. because I know this pump most likely have an overcurrent protection device anyway. So I put a 20 amp circuit and I feed it with number 12. Why 12? I don't want to use number 14. It's not a good idea, number 14. Can I have thumbs up, Chad? How we do that? Here's your other example for single phase motors. Okay. So here's the rule. Anything less than 20 amp, don't use branch circuits less than 20 amps. All 20 amps. 20 amps, the number of 12 is you cut off. That's why I up this judgment. I can go to court to prove that one. 20 amp and number 12. I don't want to use anything less than 20 amp number 12 as a branch circuit. On equipment, motors, lights, anything else. Thumbs up, Chad? Yes, no? Okay. So this is, now the last chunk of load, guys, that you're going to be dealing with is HVAC equipment. HVAC cooling and heating. HVAC equipment, remember how we did the HVAC, the cooling and heating, 440? Remember what Chad was bombarding you with all these chillers that we calculate for? Now it's time to practice it. Take this. I have a cooling unit. This is the cooling unit that you guys have in your project. This is directly from your project, cooling unit. The cooling unit is rated load amps on the nameplate is 81.6 amps. The voltage is 28 volt 3-phase. And all this information from spec page number 18, I believe. That's a spec that I gave you guys. I hope the page that's from last quarter. I hope the page didn't change. Can anybody verify the spec, guys? Is this number 18 for this year? Okay, right on the nameplate, you're going to find, guys, maximum overcurrent protection device 110 and minimum circuit ampacity 91. These are on the nameplate of this condensing unit, the chiller, right on the nameplate. Okay, now based on this, can I get you guys to understand these are spec on the nameplate of the cooling unit? So when we deal with HVAC equipment, the code says you have to use this, what's on the nameplate. Don't mess around with it. Okay, so sizing the overcurrent protection device. Do I have any option other than using 110? No, they're telling me 110. I'm plug 110. Branch circuit conductors, when I size the conductors, you size it based on minimum circuit ampacity, 91. Take it to 50, 75. That's where you got the 3 conductors, number 3. The 3 conductors, number 3. 3 conductors, number 3. Any question, guys, about this? Let me repeat myself one more time. For heating, ventilation, and air conditioning equipment, you use the nameplate. If it's condensing unit, you always use the nameplate. Okay, on the nameplate, it says rated load amps, 81.6 amps. It says 28 volt 3-phase. And the specification says maximum overcurrent protection device 110 and minimum circuit ampacity is 91 amps. 91 amps. That's right on the spec. Okay. The spec that came with the way at the end, all these description of mechanical equipment, right on the nameplate. Then from there, you have no option other than using the overcurrent protection device and using the minimum circuit ampacity for sizing the conductors. Can I have thumbs up, Chad? We fully understand that?
We didn't have to worry about around 45.
No, not with minimum circuit ampacity, no. If, now Darren and Aaron, my friend, if the minimum circuit ampacity is not here, then you take this number and what do you do with it? Multiply it by 1.25. If you guys graduate from Dunwoody, not knowing how to do this, ask me for a refund. We cheated you. No question asked in my mind. That's the difference what we graduate to as designers, not drafters. Drafters is one thing that you do. You guys be able to design. There's a lot of people in the field who would love to use you as drafters for the rest of your life. They will do the design and you will do the drafting. If you're okay with this, fine with me, but we're not okay with you being drafters only. That's what you guys are going to get into sizing for the project. We sized the feeders with me in the service, right? Last week. This week, we're going to size the branch circuits. Okay? Any question about the HVAC? And we're going to be doing this one, guys, as we move forward. It's nothing. You're going to see me talk about these all the time. Okay, so that's the HVAC. The last load, and I'm picking these loads specifically because they represent loads that you guys have. Take this. I have an electric heater, 30 kW, 2-way, 3-phase electric heater, and I need to size it. Now remember, these are equipment, dedicated circuit. Here's how we do it. Take the amp. This is my amp conductor, 1.25. Get you this from 104. Get you to number 2, and then overconduction device 1.25. Get you 110. For heaters, because they're resistive load, we use the kW to find the amps, and from the amps we multiply it by 1.25, and we size both the conductors as well as the overconduction device from the same 1.25 times the full load current of that piece of equipment. Any question, guys? So when you see your heater in your building, what do you need to do with it? You're going to apply that rule. Dedicated circuit to it, and that's how we size the circuit. So here's where number 2 is coming, and here's where number 110. Now, I hope you would keep, I colored it for you guys because I want you to keep this handy, because as we go through circuiting, Andrew, my friend, you're going to ask me, Chad, how am I going to circuit that room? This will be your criteria for circuiting. Your criteria for circuiting. Any question, guys? Any comments? Any questions? Any comments? Any questions? Now, armed with this information, Jeff, I feel sorry for you because you heard it multiple times. Armed with this information, guys, tomorrow we're going to do the riser, and we're going to load a couple of equipment, and next week, or actually, if you guys are ahead this week, we're going to start laying out our receptacles and circuiting them and our lights. Cool? I just need one, before I let you guys go as a relax a little bit. I want somebody to give me a thumbs up that we fully understand all the circuiting that we need is right here. Cool? Okay. Thank you.